Hey everybody, this is the review on isolines. And so we've talked about the motivation a lot, that if we have a field like the one below, and we did an example where we elevated that field in height, and we looked at where it intersected a plane and found these intersections, and we said that these were the isolines. It's where the field has a constant value. And we call the value the iso value. So if we took an iso value of 20, then this field has isolines for an iso value of 20 at the black locations. And so for the project, the goal is to be able to calculate these lines. And so we went through a lot of motivation in the class about why we would want to approximate it, what would happen if we had a very fine, like many-faceted version of the isolines, and that it just didn't really make sense for us in terms of the amount of cost for computation and memory, and so instead we wanted to have something that was just really coarsened, because that would save on computation and memory. And so we ended up saying that for quadrilateral, we were just going to use a line segment to calculate the isoline, a single line segment, and the endpoints of the line segment would be on the edges of the cell, and that we could calculate this endpoint exactly. And so this is really the key, is that, again, and I've already skipped the slide, but we're iterating cell by cell, and then we just focus on how to solve it for one cell. And the way that we solve it on the cell is we calculate the location at the edge. And so it'd be this is where, for an iso value of 0.5, we have one edge, and this is another iso value of 0.5, and then we connect it up with a line segment. So I'm sorry, my dog is barking in the background. I apologize if it's distracting for the video. So we spent a lot of time looking at this case right here, which is case 14. You'll know why we call it case 14 in a couple minutes, where there was one vertex that was low and the other three were high. And we talked about trying to calculate where this vertex resided, which is a big part of implementing the algorithm. And we talked about if we use different iso values for this cell, where would it be? And we looked at that solution right there. And then we started making it even more general, where instead of having field values of 0, 1, and 1, we had field values of A, B, C, and D, but A is less than the iso value and B, C, and D are greater than the iso value. And then we were able to calculate, using our linear interpolation formula, exactly where these endpoints would lie. And I noted in lecture that this cell is good because it's really simple. It goes from x equals 0 to x equals 1 and y equals 0 to y equals 1. But of course we're going to deal with cells that don't go from x equals 0 to x equals 1 and y equals 0 to y equals 1. And this formula right here is using that is x equals 0 to x equals 1, and that's where these zeros and ones are coming in. And so if it was a different location, we'd want to be updating this formula for the x and for the y. And so then afterwards, I said, well, we understand this one case, the case where we've got the low vertex is 0 and the other three are 1. And we talked about how many cases could there be, and there were 16, and these were the 16 cases. And of course, as you know from lecture, these are numbered in a special way. And but the case that we looked at so much in lecture was case 14. And then we talked about how there's some similarities between the cases. And then we talked about this ambiguous case where we just pick one solution. And so in the homework, I don't care what you pick. You can pick the solid lines or the dotted lines. And I've actually posted reference images for each. And so whichever one you pick should be fine. And we talked about what it means to make one decision versus the other. And so then the next bit of it was that we were going to pre-compute the correct answers for all 16 cases and store them in a lookup table. And so to make that lookup table, we did a little thinking. We decided that every case had 1 or 2 line segments, and the ends of the line segments are always along edges. And so then we made a convention, and our convention was that we'd have edge 0 on the bottom, edge 1 on the right, edge 2 on the top, and edge 3 on the left. You could have a different convention. That's the convention that I chose. And then this was going to allow us to represent, one of our cases. So here's case 14, and with case 14 in our lookup table, we'd say the first line segment, well, it's got two endpoints, and the endpoints are on two edges, edge 0 and edge 3, and so we would store 0 and 3. And we do that for each of the cases, and we'd store it in this lookup table. So, the correct answer for this case, there's one line segment. The line segment has endpoints on edge 0 and edge 3. Then the next bit was identifying which cell we had, and the idea there was we would go to every vertex and compare its field value with the ISO value. And so this is, and then if it's lower than the ISO value, we'd mark it with a 0, and if it was higher, we'd mark it with a 1. This example is a little weird because the field values here are 0 and 1. And so these are like floating point values, 0.00 and 1.00. And this is like a single bit, like a false or true. So I don't love that this says 0 and 0, but they actually mean different things. But you would go to every vertex and say, is it lower than the ISO value or higher than the ISO value? And then get a 1 bit, a 0 or a 1. And then the idea was to stack those bits up. And so you would put the value for V3 at the fourth digit, the value for V2 at the third digit, the value for V1 at the second digit, and the value for V0 at the 0th digit. And so in this case, we've taken the 1 for vertex 3 and put it there, the 1 for vertex 2 and put it there, the 1 for vertex 1 and put it there, and the 0 for vertex 0 and put it there. And this makes a binary number, and if you add this up, it's 0 plus 2 plus 4 plus 8, which is 14. And that's why we call this case 14. So as we go back to these 16 cases, if you were to do this same mapping, in this case right here, this would be 8 plus 0 plus 0 plus 0, so that's 8, and this is case 8. And so then, we get to put it all together at the end, which is we have our lookup table. It says for each case how many segments are there. Case 0 has 0 segments, case 15 has 0 segments, case 6 has 2 segments, and case 14, the one we study so much, has 1 segment. And we have our lookup table, and so, and again, this was just a decision. We could have arranged this information however we wanted, but I decided to arrange the information having 16 as a two-dimensional array, having 16 rows and 4 columns, 16 rows for 16 cases, 4 columns because you can have at most 2 segments, and each segment has 2 endpoints, so 2 times 2 is 4. Now, some of them don't have 2 segments, so here's case 14, and we put in 0 and 3, edge 0, edge 3, and there's no other segment, so the other 2 are just -1, saying nothing goes there. And then the final step then was to, we already saw before there was a big for loop, 4 over all cells, and then this is the case to handle a single cell. We identify the case. That means that we look at the vertices and figure out whether the values are low or high and build up our binary number to get, for example, 14. We see how many segments there are, and then for each segment, we figure out which edge it's on, and then we interpolate the position along the edge, and then we do it again, and we've gotten 2 points, and then we call a function I added for you, which is add line segment to output for the 2 points. Maybe it has a somewhat different name, but you can look through the code and figure out the exact name. And then this interpolate position along edge stuff is what we already talked about before here, where we were solving the positions of the points. So I think that's it. I think that's just kind of a whirlwind summary of isolines. But hopefully hearing me say the words again and looking at the right slides helps everyone put it together and answers what questions they may have. Good luck, everyone, on the project. Bye.